Welcome to Lecture 15, in which we discuss hidden variables and Bell's inequality. This is the material covered in the last few pages of Chapter 4 in your text. I guess I'll start this by saying that the purpose of hidden variables or the hidden variable theories arose because some people have objections, you might say philosophical objections, to the idea of quantum mechanics. After all, from quantum mechanics, we see that often we cannot say with certainty what's going to happen as the result of some experiment. Instead, the best we can do is to express some probabilities. But you need to understand that that's very different from classical physics. Let me explain what I mean. In classical physics, suppose we have some system of particles like this. And we know that we have this system of particles at time t equals 0. If we want to know where all those particles will be at some later time, maybe t naught, all we need to know is the initial conditions of this system. If we know the initial position of each particle at time t equals 0 and the velocity at that time as well, then we can, and we know all the forces acting on these particles, then we can predict where they will be at any later time. However, in quantum mechanics, as has already been mentioned, it's often the case that even though we might know the initial conditions of an experiment, we still can't say with certainty what's going to happen. And a lot of people have found this to be very disturbing. I mean, you probably have all heard the quote by Einstein that I don't believe that God plays dice with the universe. This was because of his objection to the idea of the probabilistic interpretation that quantum mechanics leads to. On the other hand, some people don't like the classical view either, and let me try to explain why. If we get back to this picture shown right here, where we postulate that if we know the initial positions and velocities of all the particles, and there's any outside forces acting on them, then we can predict where they will be at any later time. Well, that seems to lead to a situation, if you just enlarge this example, it seems to lead to a situation in which the idea of free will is challenged. What I mean is that suppose that we knew the position of every particle in the universe at some time. We knew the position and the velocity of every single particle in the universe, so that there's no outside forces. All of the forces are internal forces between the different particles. Well, then it would seem that if we could specify all those initial, at least if the classical idea is accurate, that as long as we can specify all the initial positions and velocities, that we can predict where all the particles will be at any later time. If that is correct, then that seems to say that if we knew everything about the universe at some instant in time, then we could predict everything that would happen after that. And that seems to challenge the notion that we have free will. So this is why if you look in the library, you'll see many books with topics such as the philosophical interpretations of quantum mechanics. And it's because quantum mechanics seems to have some very deep implications concerning ideas like free will and determinism. And so these ideas have gained a lot of interest even from people who are not technical, not in technical areas. But anyway, the idea of hidden variables, this is proposed, the hidden variable theories are proposed by people who don't feel so comfortable with the probabilistic interpretation of quantum mechanics. And they say, once again now visiting this idea here with classical mechanics, again, with classical mechanics, if we know all the initial conditions at some time, all the necessary initial conditions, then we can predict the state of the system at any later time. But in quantum mechanics, that does not appear to be, well, it's not true in quantum mechanics. So what some people, the advocates of the hidden variable theories, what they said was that, well, what's really going on is that the particles, or for instance, in the end of our chapter, talking about the photons have some other quantities that we don't know about. And it's only because of our lack of knowledge of these other quantities that there seems to be this uncertainty, this randomness, or this of the need for a probabilistic interpretation. In other words, when we think we have all the necessary initial conditions, and in quantum mechanics now, when we think we have all these necessary initial conditions, and yet we still must use a probabilistic thinking to predict the outcome, we're inaccurate there, because we don't know all the initial conditions. Namely, we don't know the initial values of these hidden variables, and if we only knew the values of the hidden variables, then we could predict with certainty what will happen, and would no longer need to invoke some probabilistic interpretation. That's the idea behind hidden variables. So again, the hidden variables will take away the probabilistic interpretation, and we can get back to making certain predictions of what will happen. And what Bell's inequality does, as we learned at the end of Chapter 4, is that Bell's inequality is involved in disproving the existence of local hidden variables. So I want to... anything, I really won't be talking about anything new here. I'm just going to be presenting the arguments at the end of Chapter 4. In a way, if you found the text to be maybe a little bit difficult to understand, hopefully this explanation will help a little bit. So the experiment we have at the end of Chapter 4 is the following. We have two polarizers. I'll just say polarizer 1 and polarizer 2. And each one of these polarizers can be set at 3 different orientations. And they're the same 3 orientations for both polarizers. So I will show this in this way. And I'll call the this polarization A, this polarization I will label B, and this polarization I'll label C. And exactly the same for polarizer 2. Now, the idea is that we are going to have a pair of a pair of photons that will be, and this will be an entangled pair. In fact, this EPR pair that is mentioned in the book, namely the following. Now, if you don't see that that is an entangled pair, you should certainly take a moment to review that concept. But basically what that means is that there's no way that we're going to be able to express this. So I'll just put not equal to the following. There's no way we can find A, B, C, and D to express C in this way. And so therefore, since that is impossible, this is an entangled state. These photons are in an entangled state, and the first photon will go to polarizer 1, the second photon will go to polarizer 2, and each one of the polarizers has 3 possible settings on it, and they will be set at random in one of these settings. So sometimes, there's 9 possibilities. Both polarizers could be in position A. Polarizer 1 could be in A, and 2 could be in B, or A and C, or B and A, B, 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 C, C, A, C, B, C, C. So there's 9 possible pairs of polarizations for these 2 polarizers, and we want to know we want to investigate what's going to happen in each case. Now, we're going to, in our analysis here, we're going to be trying to figure out what would happen if there are hidden variables controlling, controlling controlling these measurements. And so, the way that the book discusses this is along the following lines. Let's suppose that for one of these photons, that its local hidden variable or variables are such that its reaction to the 3 different polarizations is A. In other words, the photon's hidden variables are such that it will be absorbed regardless of which of the 3 orientations are used. So now let's look at the different the different pairs of orientations of these polarizers. As we said before, there's going to be 9 possibilities. We could have AA, AB, AC, BA, BB, BC, CA, CB, and CC. Those are now the way you should interpret this means the first polarizer is an orientation A, and the second polarizer is an orientation A. This one means first polarizer is an orientation B, first polarizer is an orientation A, second polarizer is an orientation B. First polarizer is an orientation A, second one is an orientation C. So in every case, the first letter tells you the orientation of polarizer 1, and the second letter tells you the orientation of polarizer 2. Now, we're going to assume that the first photon, the one that is going to polarizer 1, is in the AAA state. So how would that photon react in each one of these cases? Well, it's so easy. Maybe let me look at another case. Okay, the other possibilities here, I think it'll be more illuminating if I look at another case. So we'll have AAP, APA, APP, PAA, PAP, PPA, and PPP. Okay, what I mean here, this is what the book is referring to as the different equivalence classes. And that means that the local hidden variables are such that this first one means that the photon will be absorbed at orientation A, absorbed at orientation B, and also absorbed at orientation C. The second one is that the photon will be absorbed at orientation A, absorbed at orientation B, but passed at orientation C. This one is absorbed at A, passed at B, absorbed at C, absorbed at A, passed at B, and passed at C, and onward. So you can see, since there's two possibilities for each orientation, either it's absorbed or it's passed, there's two possibilities for each one, and there's three different orientations, then the total number of possibilities is 2 times 2 times 2. So here are all 8 possibilities, or 8 different equivalence classes. And so the idea is that these local hidden variables that control how the photon will react when it encounters a polarizer, they can have values, the hidden variable or the hidden variables can have values that will divide that behavior for a photon encountering these 3 possible orientations. It will divide into 8 different possibilities: absorb, 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 pass, and so on. Now let's maybe let's look down here at this possibility: absorb, pass, absorb. So let's say that photon 1 has its hidden variables such that it's in this equivalence class: absorb, pass, absorb. That means that if it encounters a polarizer in the A orientation, it will be absorbed. If it encounters, if its polarizer is in the B orientation, it will be passed. And on the other hand, if it's in the C orientation, it will be absorbed. So what will happen to photon 1, which is encountering polarizer 1? Remember that the orientation of polarizer 1 is determined by the first letter here. So in the first 3 cases, polarizer 1 is in orientation A, and we see here that for the polarizer in orientation A, photon 1 is absorbed. So photon 1 will be absorbed in each one of these first 3 cases. On the other hand, in the next 3 cases, polarizer 1 is in the B orientation, and photon 1 is such that when, as we can see from the fact that this middle letter is P, when it encounters a polarizer in the B orientation, it's passed. So for the next 3, we get P, P, and P. And then finally, for this photon, its hidden variables are such that when it encounters a polarizer in orientation C, it is absorbed. And in each one of these last 3 cases, polarizer 1 is in orientation C, so we have A, A, A. So again, to summarize, here are the 9 different pairs of orientations of polarizer 1 and polarizer 2. If the photon going to polarizer 1, which we'll call photon 1, if it is in the APA, if it has its hidden variables such that it is in the APA equivalence class, then these letters tell how it will respond in each of these 9 possible orientation pairs. Now for the critical reasoning. We have, as we have discussed before, for this entangled pair here, this entangled pair of photons, if they are measured in the same way, which in this case means if they encounter a polarizer in the same orientation, then the measurement will be the same. Now we can't say what it will be. For instance, let me make this clear. Let's say that photon 1, which is going to polarizer 1, and photon 2, which is going to polarizer 2, let's say that they both encounter that their polarizers are both in orientation A. Now, since this means that they are being measured in the same way, or with the same basis, then the result will be the same. Now, we can't say what the result will be. Maybe both will be absorbed, maybe both will be passed. But we know that both will be, the measurement result will be the same if these are this pair right here, this entangled pair. Likewise, if both of them are in orientation B, again, if both polarizer 1 and polarizer 2 are in orientation B, and we have this entangled pair, then the measurement will be the same. Again, we don't know if it will both be passed or both be absorbed, but it will be the same. And finally, the same can be said for orientation C as well. And of course, the way that a photon responds in orientations A, B, and C determines which of these equivalence classes it's in. So this argument that I've just presented means that the equivalence class for photon 1 must be the same as the equivalence class for photon 2, since they are entangled in this way and always respond to the same way when they're measured in the same way. So what this means then is that here, I'm considering photon 1 being in this equivalence class, but since it's an entangled pair, photon 2 must also be in this equivalence class. So let's see how it would react to each one of these pairs. Well, in the first pair, polarizer 2 is in orientation A. And this says in orientation A, the photon is absorbed. So this will be A. Now, in the second pair, polarizer 2 is in orientation B, and for both of these photons, whenever they encounter a polarizer in the B orientation, they will be passed. So the second photon would be passed in this case. For this one, for C, it will be absorbed. And of course, now you see we have A, P, A. That's what happens to the second photon. And since we repeat this, since we have, for the second number up here, or second letter was A, B, C, and then A, B, C, and A, B, C. So we're just going to have that APA repeated over and over. So we have A, P, A, P, A. And so this line right here tells what will happen to the EPR pair for each of the 9 possible pairs of orientations. Now, I hope that you followed that argument and now can fill out the rest of this table. So I encourage you at this point to stop the video and try to make sure that you can fill out the rest of this table, and then when you've done, we'll all come back and look at it together. Okay. So now we'll start with the top one. Now, and this will be relatively fast to do this once you get the hang of it. Remember, in these different pairs, the first letter always corresponds to what's going on with photon 1, and the second letter, with photon 1 and polarizer 1, and the second letter tells us about polarizer 2, which is, of course, receiving photon 2. So, for the AAA, that's easy. Okay, for the first three cases, polarizer 1 is at orientation A, and whenever the photon, but now the idea is now that both photons are in this equivalence class now, the AAA equivalence class, which means that both of them get absorbed when the polarizer is at orientation A, both get absorbed when the polarizer, when its respective polarizer is at orientation B, and both get absorbed when they encounter a polarizer at orientation C. So you can see that, okay, so since this first letter is A, that means that photon 1 gets absorbed when polarizer 1 is at orientation A, which is the case for the first three settings. Okay? The fact that the second one is A means that photon 1 will also be absorbed when polarizer 1 is at orientation B. And that's the case in these three. So we have A here. And then this final A means that photon 1 will be absorbed when polarizer 1 is at orientation C. And that's the case for these three pairs. So we have again A. Now let's look at photon 2. Well, remember that photon 2 is also in this equivalence class because the photons are entangled. That's key. If these photons are not entangled, we cannot claim that they're both in the same equivalence class. That is, that their hidden variables have the same effect. But since they are entangled, their hidden variables are having the same effect, and therefore they're in the same equivalence class. So, photon 2, when polarizer 2 is in the A orientation, photon 2 will be absorbed. So we have an A there, and an A here, and an A here. When polarizer 2 is in orientation B, photon 2 is absorbed there as well. So we have A. And then finally, when polarizer 2 is in orientation C, again, photon 2 will be absorbed. And so we have A. Now, for this next one, how this will go to make it quick, you get to where you don't even have to think about it. We can say this is AAP, so we have A. That's the first A, and then the second A gives us A, and the last P gives us P. These letters describe what the first photon is going to do. And now for the second photon, we have A, P, P, like that. Okay, so if already we've come up with some different answers from what you had, maybe now it's clear what to do, and so now I give you a second chance to stop the video, try to correct any mistakes that you might have had, and then resume. Okay, so now for the next one, A, P, that's for the first photon. And for the second photon, A, P, A, P, P. And so now I'll go ahead and stop the video myself and fill out the rest of this table so that you don't have to watch all of that. Okay, so I hope that after you attempted this for the last time that you got all of these results for the table. Now, the first thing I'd like to point out to you, and this is not a surprise, it's something we've already said, but just to emphasize it now. Notice that when the two polarizers, okay, well, maybe I'll put this as a question. Okay, we've said that when the two polarizers are in the same orientation for this entangled pair, the measurement will always yield the same result. The measurement on the two separate photons will always measure the same result. Now, where is that information in this table? Think about it for a moment. Maybe even stop the video and then come back when you think you have the answer. Okay. Well, the information about what happens when the orientations are the same is all contained in this column and this column and this column. This first one is when both polarizers are at orientation A. The second one is when both polarizers are at orientation B. And the third one is when both polarizers are at orientation C. And notice that for every single equivalence class, in other words, regardless of what the hidden variables might be for each of the two photons, what happens to the two photons is always the same in these three cases where the two polarizations are the same. So either they're both absorbed, or they're both passed. Same thing here. Both are absorbed in the first two cases, both are passed in these two cases, both are absorbed in these two cases, both are passed in these two cases. And here, both are absorbed, both are passed, both are absorbed, both are passed, both are absorbed, both are passed, both are absorbed, both are passed. So we see that indeed, just as we have already known from measurement, everything we've set up here is consistent with the fact that the hidden variables being the same for the two photons is consistent with the fact that they will always be if they are measured in the same way, then the measurement will yield the same result for both of them. And again, that is only true because they are entangled. If they were not entangled, that would not be true. Now, that's all that we're going to say about those three columns. Bell's inequality deals with the situations when the orientations are not the same. So Bell's inequality deals with the columns corresponding to situations in which the polarizers have different orientations. So, in other words, the uncircled columns. Okay, so now, as was just mentioned, Bell's inequality deals with what's happening when the orientations are not the same. And in your book, they use this notation PAB to denote the probability that the measurement will have the same result for the two photons when one polarizer is at A, orientation A, and the other one is at orientation B. Or PAC is the probability that they will have the same measurement when one is at A, when one polarizer is at A and one polarizer is at C, and here's the probability when one polarizer is at B and one polarizer is C. Now, you might, if you're really paying very close attention, you might already have a hesitation. You might say, wait, what are we talking about now? Probabilities. Because with the hidden variable theories, and we are here assuming hidden variables, remember, with the hidden variable theories, that was supposed to take out all probabilities. We were supposed to be able to predict with certainty. Well, that's still the case. You're going to see all these probabilities are equal to either 0 or 1, and we just want to see which it will be in every possible case. So here for the AAA photons, and once again, remember that if one photon in the pair is AAA, then both must be, because they are entangled. So, if both of our photons are in this first equivalence class, the AAA equivalence class, then the probability that the measurement will yield the same value when one polarizer is in position A and the other one is in position B. Well, you can see when one is in A and one is in B, and you can either look here in AB or here in BA, it's the same thing either way, we get AA. In other words, the measurement is the same, is absorbed. The measurements agree. And so the probability that the measurements will agree, and now this again is only for photons in this first equivalence class, but the probability that the measurements will agree when one polarizer is in orientation A and the other one is in B is 1. For if one polarizer is in orientation A and the other one is in orientation C, what is the probability? Well, again, you can look at AC or CA. Either one tells you that they will agree. So again, that probability is 1. And then finally for BC or CB, again, A and A, they agree. A and A here, they agree. So 1. Now, what about for the next equivalence class? Well, if one polarizer is in position A and the other one's in B, then here we have A and A, so they agree. Probability is 1. If one polarizer is in position A and the other one is in position C, okay, here they do not agree. And you can see this is true either for AC, it's also true for CA. Because of the symmetry here, we really don't need to check both. You can see that when one is in A and one is in C, different things will happen to the two photons. They will not be measured the same. And therefore, this probability, the probability that they will be measured the same is 0 in that case. And when one is in orientation B and the other one's in orientation C, okay, BC, we come right here. And again, BC, A and P, one is absorbed, one is passed. So different things, they're measured in different ways. And again, you can look at BC, look at CB, you come up through the same conclusion. So we get a 0 there as well. Now, you go ahead and fill in the rest of these, and then we'll do it. Then I'll let you see the results that I obtained. Now, if you fill out the rest of this table, these are the results that you obtain. And if you did not obtain those results, please take a moment, stop the video, and go back and check your work. Now, the important point here, as far as Bell's inequality is concerned, is that in each one of these cases, so for each one of the different equivalence classes, we have at least one value of 1 over here on the right. Here we have 3 values of 1. Here we have 1, 1, 1, 1, 1, 1, and then 3 values of 1. Now that's, as the book points out, that's really not surprising. If we had been really on top of it, we could have predicted that in the following way. There's 3 different pairs of orientations here, basically, that we're thinking about. And remember that when the 2 orientations agree, these photons will always be measured in the same way. It's only when the orientations are different that they may be measured in a different way. But suppose that they're different for A and B. Well, this means that one is absorbed and one is passed for the AB or BA orientation. Now let's suppose in that case that that just means that different things happen when the photon encounters a polarizer at orientation A or polarizer B or orientation B, and the same can be said for A and C. Now, if it's true, if it's different for A and B and different for A and C, then it must be the same for B and C, because there's only 2 different ways it can react. It can either be absorbed or passed. So if they don't agree here for A and B, that means one is absorbed and one is passed. And if they don't agree here as well, then that means that C and B must be the same. In other words, let me just give an example here. For instance, in this case, if we look at this case right here, for A is absorbed, and for P is passed, and for C it's passed. So if one is at A and one is at B, we don't get agreement. If one is at A and one is at C, we don't get agreement. But then at B and C, we do get agreement. So that's all that's being said here, is that so you can just, if you wanted to, you could just look over here at the letters and predict these probabilities. So AB, yes, they're the same. So we get a 1 there. What about AC? Yes, A and C are the same, so we get a 1 there. And what about B and C? B and C are the same, so we get a 1 there. But here for this next one, okay, A and B are the same, so we get a 1 here. A and C are not the same, so we get a 0 there. And B and C are not the same, so we get a 0 there. Or let's maybe go down here just for this one, just to make sure you understand the argument. Okay, so A for this row right here, A and B are not the same, so we get a 0 here. A and C are not the same, so we get a 0 here. But B and C are the same, so we get a 1 here. And again, since there's only 2 choices for each one of these, at least 2 of them must agree. If A and B don't agree and A and C don't agree, then B and C must agree. Or likewise for the other, possibilities of that argument. But any way you look at it, we conclude that in each possible situation, in other words, in each one of the equivalence classes, we're going to get at a total here. If we add these numbers together, we will always get a total that is greater than or equal to 1. We would get 3 for the first row, 3 for the last row, and 1 for each of the other rows. And of course, these 8 equivalence classes, they are all of the possibilities. So we'll just summarize this by saying, for each equivalence class, PAB plus PB, AC, because we could write this in any order, but just to be consistent, PAC plus PBC is greater than or equal to 1. And since this is true for every class, it must be true for all entangled pairs, entangled EPR pairs. However, experiment shows, and this was discussed in our last lecture, experiment shows that when A is equal to negative 60 degrees, B equals 0 degrees, and C equals positive 60 degrees, P AB plus P BC, AC plus PBC, we found in that case for an EPR pair that the total is 3/4. And this is simply inconsistent with the local hidden variable theory. So local hidden variable theories must be incorrect. And therefore, that indicates that again, quantum mechanics does explain this result. The local hidden variable theories do not. And so, I hope that this discussion will help you understand better the material at the end of Chapter 4. And now let's think about some problems. Okay, so here are our problems, and these are perhaps the two easiest problems we've had in the entire course, but still I hope that it will help to drive home some of these ideas. Now, this first question, I realized that you could get the answer simply by scrolling up and looking at the table that we just created, but I hope that you won't do it in that way, that you'll try to think this through and try to work this out in your head. But the question is, for which equivalence classes will PAC equal 1? And answer A is in the equivalence classes AAA, APA, PAP, and PPP. Answer B is AAP, APP, PAA, PPA, and so on. You can read the rest of them. In each case, 4 equivalence classes are listed, and I want you to identify which one of these answers is correct as being a list of the equivalence classes for which PAC will be equal to 1. And then in question 2, I ask, as we saw above, for Bell's inequality, if we have an entangled EPR pair, then PAB plus PAC plus PBC is greater than or equal to 1. So the minimum value of this expression for an entangled pair, the minimum value is 1. What is the minimum value of this expression for an unentangled pair? Is it 0, or 1/4, or 2/4, or 3/4, or 1? So I'll give you a hint. What you should do is come back up to this table and think, okay, if one photon could have one equivalence class and the other photon could have a different equivalence class, then, you know, in how many situations must they agree? And so you can, you could get your quantities here. So what would be the minimum value for PAB plus PAC plus PBC for an unentangled pair? That's the second question, and then I'll try to come up with one more question in class. It's a little bit difficult to come up with questions for this material, but I think it is worthwhile, and it is definitely a very interesting concept. So that concludes Lecture 15, and good luck.